So welcome back to the fourth lecture of module 5. So in the last lecture, that is in the uh, third lecture, we have seen a laboratory type DC potentiometer. And what if the situation is that, see, what if the potentiometer has to measure a voltage greater than 1.5 volt, then how do we how do we measure such a voltage using a potentiometer? So that we have a volt ratio box. We have seen how a volt ratio box works. A volt ratio box is simply a potential divider network. So we can apply any voltage greater than 1.5 volt to the potentiometer. If the voltage to be measured is within 0 to 1.5 volt, it's not at all necessary to have a volt ratio box. But if it is greater than 1.5, any voltage greater than 1.5 can be measured using a potentiometer by having a volt ratio box in between. So today we'll see what are the different applications of DC potentiometer. And one major application of DC potentiometer was to measure the unknown voltage, and it is so that was the major application. And this I mentioned that DC potentiometer is an absolute standard for voltage measurement. Absolute standard. Why it is called an absolute standard? Because it follows null deflection method. It does not load the source, so the voltage drop inside the potentiometer under the balance condition is 0. That is why it is considered as an absolute standard. So absolute standard means we can calibrate any instrument, a voltmeter for instance, against the DC potentiometer. So we have a standard. We always try to compare our meter with a standard. So that standard is actually DC potentiometer. So the calibration, we are very well known with the term called calibration. That is, we are comparing the measurement of an instrument with an absolute standard. So here we'll calibrate three instruments, that is voltmeter, ammeter, and wattmeter. So remember one thing, even though it is a DC potentiometer, we can calibrate all voltmeters, ammeters, and wattmeters if it is MC, MI, and electrodynamometer type. So all three types of instruments, voltmeter, ammeter, and wattmeter, with different classes like MC, MI, and electrodynamometer types can be measured, can be calibrated using a DC potentiometer. And today, on the first, we'll see how to calibrate a voltmeter. So this is how we calibrate a voltmeter. It's a very simple circuit, very simple circuit. So here we can see that, see, this is the circuit. So we have the voltmeter here, which is to be calibrated, and that voltmeter is fed from a stabilized DC power supply. Stabilized DC power supply is also known as a regulator power supply. So what is a regulator power supply? That is, this regulator power supply will be taking power from an AC. So that AC will have some fluctuations. So that fluctuation should not come inside the circuit. If that fluctuation is allowed to pass to the circuit, then it will affect the voltage here, that it will affect everything. So we are keeping whatever variation here, we are keeping it away from the circuit. So this stabilized DC supply will actually keep the DC output voltage a constant throughout, irrespective of the changes in the AC supply here. So so this is for the fine adjustment, and this is the coarse adjustment. So anything we have a fine as well as coarse adjustment. So we apply some voltage, some non-voltage. Here it is, we can assume that we are applying a voltage very close to 150 volt, and we are setting a voltage very close to 150 volts, and this voltmeter will certainly give that reading here. So we have a voltage reading at this voltmeter. So that voltmeter reading we first record, and then we have the volt ratio box. So this voltage, the same voltage which is measured by this voltmeter, is actually passed to a potentiometer through a volt ratio box. So we know how the volt ratio box acts. So any voltage will be converted into a voltage within 0 to 1.5 volt. So we get a voltage after balancing we get a reading in the potentiometer which is within 0 to 1.5 volt, and that voltage is converted to the actual voltage by some multiplying factor. So that is the actual or the true value of the voltage, and that true value is compared with the reading of the voltmeter. Okay, so we take some more readings, we take as many readings as we want, and we plot a graph against the true value and the actual value, so that we get a calibration curve of this voltmeter. So this calibration curve will actually help us to know what is the accuracy rate of the voltmeter for various readings. So this calibration reading the graph will help in making proper adjustments in the voltmeter or proper adjustments in the reading of the voltmeter, so that we are very much close to the true value. So this is how we calibrate, this is how we compare this reading of the voltmeter with the potentiometer. So this is a very simple circuit. Actual voltage we are measuring, we are getting the true value from the potentiometer, and that is being compared with the actual value shown by the voltmeter. We take so as many readings as we want, and we plot a graph, and that graph is called a calibration curve, and that is how we calibrate a voltmeter. Now same thing we can apply for an ammeter. So very simple adjustment, very simple circuit, but here we do not require a volt ratio box because we are going for ammeter. That is, we are measuring the current only. So here also we have a coarse adjustment and a fine adjustment. For passing a current, we have to have a closed path. So this is the main closed path, which is, so this closed path is circulated by a current from a stabilized DC source, and here also we have a coarse adjustment and a fine adjustment. And one thing is that we cannot directly give current to a potentiometer because potentiometer accepts only voltage. So by keeping a resistor here, this resistor will carry this current. So when current passes through resistance, certainly there will be a voltage drop, and that voltage drop is passed to the potentiometer. So we cannot directly give current to the potentiometer, rather we connect a resistor through the path of the current, and that current will cause a drop in the resistance, and that drop is fed to the potentiometer. And what is the current then? The current, actual current, the true value of current which is measured by the potentiometer is nothing but Vs divided by S. So what is Vs? Vs is actually the drop across the potentiometer. So how do you find Vs? We balance the potentiometer so that we get the value for Vs. So that is Vs. So Vs divided by the non-standard resistance. So this S value is non, and Vs divided by S. So Vs is actually calculated from the balanced potentiometer. That value divided by the standard resistance, we get the value of current. Now imagine there is a situation we can directly get the value of current from the voltage. That is, if suppose the standard value of resistance is kept as 1 ohms, so Vs divided by 1 ohms is nothing but Vs. So then we'll get I is equal to Vs. So whatever is the reading of the potentiometer will be the true value of the current, and that current value, the true value of the current value obtained in this way, is being compared with the ammeter reading. So we can check, or we can compare the reading of the ammeter with this true value. This is the true value I, and we can take as many readings and plot a graph, and that graph is called the calibration curve, and we can actually compare the ammeter reading for various true values of voltages, so that we'll get an idea how the ammeter behaves at various stages. So this is how that goes. And the last application, so we have C2 applications, voltage and current. So if we can measure voltage and current, or if you can calibrate voltmeter and ammeter, then certainly you can calibrate wattmeter. So before going to the wattmeter, we'll see one thing, that is how the power is measured using a potentiometer. So we have a figure. So this is the figure. So we have a supply. This will be a stabilized supply which supplies a current, and we have a load also. So the voltage drop across the load is given to the volt ratio box, and the output of the volt ratio box is given to the potentiometer. And likewise, so this is actually the same procedure that we followed for the calibration of voltmeter, and this is the same procedure that we have seen for the calibration of ammeter. We have a standard resistance, and the standard resistance, the voltage across the standard resistance is taken to the potentiometer. So we have a changeover switch here. If the switch is connected to the standard resistance, then we'll get a voltage drop, we'll get the voltage drop across this resistance. Knowing the value of resistance S, we can get the value for I. And by closing the switch to this point, we can get the voltage the voltage across the potentiometer. By having that voltage across the potentiometer, by multiplying that value of the potentiometer voltage to by a scaling multiplying factor, we'll get the actual voltage here. So two ways. One is after closing this switch, we'll get the voltage drop across this resistance. That voltage drop divided by the resistance value, you get the current value. And the actual voltage across the load can be calculated by balancing the potentiometer. So that balanced potentiometer value, after balancing the potentiometer, the voltage is multiplied by some multiplying factor so that we get the actual voltage. So knowing the voltage and current, we can get the measurement. We can get the value of power. What is power? So I is nothing but Vs divided by S. Vs divided by S, the drop across the resistance divided by S. And what is V? The voltage across the potentiometer after balancing, that is VR, multiplying by some multiplying factor, we get V. So V into I, we get the value for power. Now same purpose, same principle can be carried forward to the calibration of wattmeter. So one disadvantage of this circuit was it actually loads the source. We have to take the current. This current is actually drawn from the supply. So supply has to bear this current value. Suppose if you have a voltmeter, if we have to calibrate a voltmeter of higher range, for example, higher amps range, that is 20 amps or 15 amps, then this source has to drive that high current value. So that will cause so many drops or the losses in the circuit. So that this circuit is normally not preferred for the calibration of a wattmeter. Instead, we prefer a phantom loading. I hope you all know what is phantom loading. That is fictitious loading. That is, the meter thinks that it has the actual load, but that is not the case. That is, the pressure coil of the wattmeter will be supplied from the actual voltage from the source. So this pressure coil, two ends are connected across the actual supply voltage. So this is the high voltage supply. So that pressure coil will actually have the high voltage, the normal its standard voltage taken from the high voltage supply, and the current coil carries current from which is driven by some other source, an independent source, which is a low voltage supply. So this circuit, being a low impedance circuit, can take a high current value. So this phantom loading will have so many savings, that is losses is very less, because we are using an independent supply, a low voltage supply, and the low impedance circuit can have a higher value of current, and this current value is not taken from the normal supply. So this circuit is more or less effective or more efficient than the previous circuit. Now the principle is the same, that is, we have a standard resistance here. So that voltage across the standard resistance divided by a voltage across the standard resistance, we can get it from the potentiometer. That divided by the standard resistance value, we get the current value. So that is there. And then the potential, the drop across the pressure coil can be calculated from after placing the switch to this point, and that can be obtained by balancing the potentiometer. That potentiometer reading multiplied by the multiplying factor, we get the actual voltage. So that actual voltage multiplied by the actual current will give the true value. And we have seen this is a DC supply, so the cos phi value, the power factor will be 1. So V into I surely get the true value. So the true value is there. So true value is being compared with the wattmeter reading. So the true value obtained, that is, first we are placing the switch to this position, so that we'll have a voltage drop here. That voltage drop divided by S, we get the current value, and then we place the switch to this position. We'll balance the potentiometer. We get the voltage. That voltage is multiplied by a multiplying factor, and we get the actual voltage. So that voltage multiplied with the current will get the true value of power. That power is compared with what? The actual compared with the wattmeter reading. So again, we can follow the same procedure. We can actually have as many readings and plot a calibration curve, so that we'll have a broad idea of how the wattmeter behaves in various situations. So that is how the wattmeter is being calibrated. So this is how the things go, and the main principle used here, it is phantom loading. So today we have seen three things: applications of DC potentiometer. Thank you.